That's a question. I don't know. Why don't you try and plug some numbers in and see what happens? What happens if you plug in 2? You get 1 over 3. So you get 1/3. Okay. What happens if you plug in 3? 2, so 4 over 8. Yeah? Maybe it is. Maybe we could show this is true. How about we do this? N squared minus 2n plus 1. I expanded the numerator. Is that less than, now multiply both sides by this denominator, n squared minus 1. Is that true? See what I did? So now let's move things over. These would cancel, right? And we would get, how about we move this to this side? And let's move this to this side. So we get 0 over here. We get 2n, and then minus 2. Yeah. Oh, yes, okay, but we're going back to that whole thing with n. If you plug in 1 for, if n was 1, right? If n was 1, then you would stop at here. You would stop here, so you wouldn't get to that.
So there it has to be 2, n minus 1 has to be 2.
That's right, exactly, yeah. Yeah, so doesn't this look like, let me move this 2 back over. 2 is greater than 2n. Then that would mean, divide both sides, that n would have to be greater than 1 for this to be true?
Yeah.
Like for this to be true, we need n to be greater than 1. So can you see how this can get kind of messy? Because all I've done is asked about this one. I then need to go ask about that one.
Yeah.
Right? Be the same, right? It's not the same, though, because this one's n minus 2. This is n minus 2 squared. Right? So when you expand that out and then do the algebra, it's going to be different. Now, there's a way you can do this, but it's just beyond, it's beyond what we want to do right now, okay? I was just curious if we could come up, I more wanted you to see the difference between these two expressions, all right? All right, let's move on. I'm leaving this as kind of a, Do you want to have the computer graph it real quick and see what it does? Let's see if the computer gives us an idea. What was it? N factorial squared, right? So n factorial squared over n squared factorial. Oh. Well, how about that? Boy, that looks like that converges to 0. Why? This is going to 1. I think this is going to be less than 1, less than 1, less than 1. And then that very last one, I could leave alone and not touch it and leave it as 1 over n squared minus, I don't know, something, and then just squeeze it down between 0. Don't worry about it. Don't worry about it. All right, the next definition there in front of you has to do with sequences. And if sequences behave a certain way, we call them increasing or decreasing. And this is not a very far stretch from the whole idea of increasing and decreasing functions from college algebra and calculus. So I think we can go through this pretty quick. Right? If a sequence is said to be increasing, if a sub n is less than a sub n plus 1. So look at what that's saying. That's saying if I go to the nth one, so let's say I go to the 10th one, right? This is just saying that the 10 plus 1, the 11th one better be bigger than it. So the 11th one better be above it. So if I keep doing that for every n, it keeps going up, right? Then it's increasing. Then if you flip the inequality over, and you say that the nth one has to be bigger than the next one, then now it's got to be going down. So it's decreasing. Pretty straightforward. So in either case, if you have a sequence that is increasing or a sequence that is decreasing, in either case, we call that a monotonic sequence. So if somebody says, hey, yeah, you've got the sequence and it's monotonic, that means it's either increasing or decreasing, one or the other, all right? A sequence, A sub n, is said to be bounded above if there is a number, capital M, such that the sequence is always less than or equal to m for every little n bigger than or equal to 1. All this is saying is go anywhere you want, go look at your point, it's going to be smaller than or equal to some capital M. So it is bounded above. It's like there's a ceiling, right? Your sequence never goes above that ceiling. In that case, you're bounded above. On the other hand, if you have a lowercase m, such that your sequence is always bigger than that one, that little m, all the time, then we will say that we are bounded below. So you got like a floor that you can't go below, right? Now this, you know how we said with monotonic? Monotonic meant it could be one or the other?
Yeah.
Okay, this last thing at the end of this, if we say that a sequence is bounded, what we mean is that it's bounded above and below. And below. Both. Okay? That's important. It's very important that we understand that. With monotonic, it means it's either increasing or decreasing. But with bounded, it means it's got a floor and a ceiling. Okay? It's trapped between two numbers, or sequence. All right? That's why I highlighted or bolded out that and. With me? Okay. And that brings us to the very important theorem called the monotonic sequence theorem. And it's a very simple statement. Every bounded monotonic sequence is convergent.
But it doesn't mean that if we get a little m, we'll always have a big m, or the other way around, right?
That's right. A sequence does not have to have an upper. Sequences don't have to have bounds. Okay? You can have a sequence that has an upper bound and no lower bound. You can have a sequence that has a lower bound and no upper bound. If a sequence has both an upper and a lower bound, then we call it a bounded sequence. All right?
And they all
Not all bounded sequences converge. A monotonic bounded. Okay, so these are very strong. This right here is a very strong condition, right? That right there says that our sequence is stuck between a capital M, heads up. I just rimmed it out over there. That marker's not much better. That's okay. Little m, right? So this theorem says every bounded, okay, so this would be a bounded sequence, right? Both an upper and a lower bound. Every bounded monotonic. Monotonic means what? It's either increasing or decreasing. Let's look at one case. Let's say that our sequence is increasing. Okay, so that means I go to my first, I plug in 1 and I get some point, right? Okay, so I get some point. There you go. Now, the next point I draw has to be what? Bigger or above that point, right? So my next one has to be above that. And then, next one above that, and above that, and above that. But I can never go above this, right? So that means that it's got to converge to something, right? It's like a horizontal asymptote. Okay? Now we are not saying that M is the horizontal asymptote. Be careful with that. We are not saying that M is. We might actually have a different line, let's say this, and that would be our limit of our sequence, wouldn't it? Okay, so, but the thing is, you can't come back down, right? Because it's monotonic increasing, right? So what about if it were decreasing? Same thing the other way, right? If it were decreasing, then you would have some boundary here. You can't go below. This would be your limit, and so it has to converge. Now, why is this monotonic sequence theorem important? Sometimes We just want to know whether or not a sequence converges or diverges, one or the other. We don't necessarily care to know even what it converges to. All right? So I give you a sequence, we look at it, and we're like, does it converge or diverge? A lot of times you can't do them, but if you can show it's bounded and you can show it's monotonic, then you know it converges. So what would it mean for me to show that a sequence is bounded? What would I have to show? There's a number that's always bigger than it, a number that's always smaller than it, right? And then to show it's monotonic would mean I have to show that it's either increasing or decreasing. So let's see if we can do an example where I use both of those. I want to do one that's somewhat like one here. Yeah, let's do this one. Where'd it go? Use the monotonic bounded sequence theorem to show a sub n equals 2n minus 3 over 4n plus 1 converges. Now let me say something here. If I asked you right now whether or not this thing converges or diverges, everyone in here should be able to tell me it converges to 1/2. And that you just say, oh, this I could switch to a function of x, use L'Hopital's rule, I'd be done. I get it, okay? That's not the point of this exercise. The point of this exercise is to show you how we use theorems to show something's true. And this is more important than the fact that you could get this answer without this work. So after I'm done with all this, I don't want to hear anyone raise their hand and say, could I have just done the limit? Because you're missing the whole point. The whole point is I'm about to do things right now that are a little bit mathy, that make you have to think logically, and that's where we're headed in Chapter 8. We're headed to where you have to prove things. Like a lot of the hard problems I'm going to give you later, I'm going to give you this thing called a series, and I'm just going to ask you it's like flip a coin almost. Converge or diverge? That's all I'm going to ask. And you have to prove to me which one it is. And your proof is going to require you writing down logical steps in defending each step and making it make sense to me. That's what I'm about to do right now. So this is our first true exposure to how you use theorems to show things are true. All right? Ready? All right, so I'm supposed to use the monotonic bounded sequence theorem. So what do I want to show? So first I'm going to write is WTS, which stands for want to show. All right? Now, actually, that's not my own thing. In mathematicians use WTS all the time. All right? I want to show that A sub n is bounded, right? And what else? Monotonic. If I show that, if I show those two things, I'm done, right? Because the theorem says if your sequence is bounded in monotonic, it does what? It converges. Now, does that theorem tell us what it converges to? No, but that's not what I'm being asked. I'm just asked to show it converges, all right? All right, so let's tackle these one at a time. First one, I want to show A sub n is bounded. how do I show that? Well, here's what I have to show. First, I have to show that there exists a number that's always bigger than my sequence, right? And then there's a number that's below, that's always lower than my sequence. It was capital M and little m, right? So first thing I want to do to show that it's bounded is to show that there exists. That's a capital E written backwards. That stands for the words there exists. All right? I'm showing you more mathy language, more symbols, all right? So I want to show this is a, you go look in a textbook, if you ever see that capital E backwards like that, it means there exists, all right? So I want to show that there exists a capital M such that A sub n is always less than or equal to capital M. I want to show that there's some number that's always bigger than my sequence all the time, right? Okay, well, let's take a look at our sequence for a moment. Maybe we can figure out a number that's bigger than this. And it might be worth it for us to actually write down the first few terms of this. Okay, so maybe I should do that over here. What are the first few terms of this sequence? We plug in 1, we get negative 1 over 5, negative 1/5. Next one, plug in 2. What do we get when we plug in 2? 1/9, right? Plug in 3, 6. So we get 3 over 3 here, 12, 13. And I'm thinking 1, right? Are you thinking 1? I don't think that gets bigger than 1. What is it converging to? Like if we did L'Hopital, what does it look like it's converging to? It would be 1/2, right? So I need to show that there's a number that's always bigger than that. I'm writing out the first few, and I'm going to kind of make a guess now. I think it's 1, all right? I think my sequence is always less than 1, right? But I have to show it, all right? I have to show it. So here's what I'm going to do. I need to show that there exists an M such that this is true. I'm now going to establish what I think that M is. Let M be 1, okay? Do you understand why I'm picking 1? These are all fractions that look like they're smaller than 1 to me, right? All right, so how can I convince you that our sequence is always smaller than that? Then 2n minus 3 over 4n plus 1, I need to show you that that's true, right? I need to convince you now that that's true. Is this true or not? So I'm just going to do some algebra now, all right? I'm going to do some algebra on this. This implies that 2n minus 3 is less than or equal to 4n plus 1. So I just took this inequality and multiplied both sides by the denominator here, right? Cleared out the fractions. And now let's try and get n by itself. So I'll subtract 2n here. I'm going to subtract 1 there. Subtract 1 there. What do I get on the left side? Negative 4 is less than or equal to 2n. And now let's divide both sides by 2. And you get negative 2 is less than or equal to n. Now what does this mean? This means that in order for this to be true, right? In order for this to be true, what I need to be true is that I need n to be bigger than or equal to negative 2. This is true so long as this is true. Now, is this true? Yes, because n is coming from the natural numbers, right? 1, 2, 3, 4. So this is always true, which means that that's true, which means that I have found an upper bound.
Couldn't you say M is 1,000?
Yes. You could have let m be anything you want, but it needed to be bigger, right? So what if you had let m be 1/2? Let's just see, just real quick. What if we would have said 1/2 here? Then we would have multiplied both sides. We still would have got this, right? This would have come over here, but then I would put 2 over here, right? Which would have made that a 4, and this is 6. And now when you do the algebra, what do you get? Oh, wait, did I do that right? 2 less than or equal to 2 4m. Are my 4's canceling here? That doesn't make any sense. I did something wrong. Hold on. Well, crap. You know what? It is then. 1/2 would have worked. This sequence is approaching 1/2, right? Converging to 1/2, but it's coming up from below it. I was expecting it was going to come up from the top and bottom to it, like this. But yeah, do y'all see what happens? I was starting to freak out because look, what do we get when we cancel those? 1 is bigger than -6. That's true. Okay? Which means this is always true. Okay? So, yeah, hold on. Sequence, let me put it in here just so you can see what I'm talking about. It's 2n minus 3 over 4n plus 1. Okay, so if I graphed, yeah, see? It's approaching 1/2 from the bottom the whole time. So that's 1/2 is an upper bound. So you couldn't pick any number. What number would not have worked? 1/4 wouldn't have worked. Okay, 1/4 wouldn't have worked. If I would have put 4 here, to do that instead, then this would have been 8, and that would have been 12, and then you would have got some ridiculous statement here like 4n is less than or equal to like 13, and that's not always true, right? As n gets bigger. Yeah, so that wouldn't work. Okay. Does that address your question in some way? Yes, 1 worked. We could have used 1,000. We could have used 1/2. Those are all upper bounds. Okay? Now, I still need to show it's bounded below, right? That was the first thing I wanted to show. Nope, doesn't matter. Nope, just has to be an upper bound, that's all. Okay, I want to show it's bounded. So first of all, I wanted to show that it was bounded above. We got that? Now I got to show it's bounded below. So step 2, I want to show that there exists a little m such that a sub n is always bigger than or equal to little m, right? So do you have a candidate for little m? Go back to here. So we have a negative here, don't we? So we can't use 0. But -1 would be below it, right? So let's go with -1. So let little m be -1. And then we write down the inequality. We need this to be bigger than or equal to -1. And we're more asking ourselves the question of whether or not that's true, right? Yeah. So then we multiply both sides. We get 2n minus 3 is bigger than or equal to -4n minus 1, because that negative passes through. Move all my n's to one side, so 6n must be greater than or equal to 2. Are y'all following that? Just algebraically manipulating this. This comes over here, this comes over here. And then divide both sides by 6. And you get 1/3. N must be bigger than 1/3. Is n bigger than 1/3? Yes. N is going to be 1, 2, 3, 4. So this inequality is true. This is true as long as n is bigger than 1/3. So we have found a lower bound, haven't we? So we wanted to show it was bounded. Check. Are we done? Now we have to show it's monotonic. And monotonic means increasing or decreasing, which means we have to actually figure that out ourselves. We have to determine that. Guys, you all right over there? All right. We have to figure out whether or not it's monotonic increasing or decreasing. So I now want to show a sub n is monotonic. Now we already cheated by looking at the picture, didn't we? But how would you know that it's increasing from this? Well, it went from negative to positive. That's a good indicator, right? And you could convert these maybe to decimals to see that they're getting larger. I'll tell you all a story in a second. All right, so monotonic, we think it's increasing, right? Okay, we think it's increasing. So I want to show that a sub n is increasing, which means I want to show that a sub n is less than a sub n plus 1, right? That's what I want to show. Doesn't that mean increasing? Yeah. The nth one, let's say this is the nth one, is always smaller than the next one. N plus 1 would be this one, right? Yeah. So how do we show that that's true? I mean, we can't just say, oh, look, obviously it's true. That doesn't work. So watch how we do this. What is a sub n? 2n minus 3 over 4n plus 1, right? I want to show that that's less than what? A sub n plus 1. Yeah. That means you're going to plug n plus 1 into the sequence. Doesn't this mean just plug n into the sequence? Yeah. This means plug n plus 1 into the sequence. So I'm going to write the sequence 2, parentheses, n plus 1 minus 3 over 4 n plus 1 plus 1. It's like you're evaluating a function at a different point. Like this is like f of x, and this is f of x plus 1. And I want to show that this is true. I have to show that that's true. More algebra, right? Yeah. Okay. So 2n minus 3 over 4n plus 1 must be less than, distribute. What would that new numerator be there? 2n plus 2 minus 3? 2n minus 1? Yeah. Okay. What would my new denominator be? 4n plus 5. Right? Now what? Yeah, like a cross multiply. You're going to clear the fractions. You're going to multiply this side by 4n plus 5, this side by 4n plus 5. This side by 4n plus 1, this side by 4n plus 1. Essentially, this is going to multiply to here, and that's going to multiply to here. And you're going to clear the fractions out. So we're going to have 2n minus 3 times 4n plus 5 less than, do I have to worry about flipping that inequality? We just multiplied, right? We know that this right here and this right here are always positive because n is a positive integer, so that's perfectly legal to do that. And now, expand. At the end of all of this, what I'm hoping for is the final statement that I have is true, okay? If the final statement I have is true, then my assumption that this was the case is true. So let's see here. Distribute through here, I'm getting 8n squared minus, let me see, 8n squared minus, no, plus 10 minus 12, so minus 2n. And then minus 15. I want that to be less than 8n squared plus 2n minus 4n is minus 2n. And then finally minus 1. Y'all can check my math there. That look okay? Lots of good things are about to happen. If I subtract 8n squared from both sides, they both go away. If I add 2n, they're both going to go away. And my final statement is that negative 15 is less than negative 1. And that is true always. Right? Therefore, my assumption that it was increasing is true, right? So we're done. We have shown that this sequence is bounded, which required showing is bounded above and below. And then we show that it's monotonic increasing by showing that this inequality was true. And there's no shortcut around, that's the way we would have to do it. All right, if you're trying to use the theorem to show something. Okay, that concludes 8.1. All right, so I'm going to tell you all a quick story here. I've got 10 minutes while I'm erasing the board. When I first started teaching here at Northwest Vista, They had us out in the portable buildings, and I had a colleague of mine that we officed together. Now let's just say the two of us together just out of graduate school, we were complete math dorks. I mean, just really, really bad. And so he was trying, I don't know, we were just sitting there talking one day, and he was telling me that he had told his girlfriend that his love for her was that the derivative of his love was always positive, is what he had told her. So you understand what he was trying to say to her? What was he trying to say to her? The slope of his love function was always positive, is basically what he's saying, right? So like, the idea is, I guess, that if this is time, and this is love, okay? He's saying that if you look at the graph of his love for his girlfriend, that the derivative was always positive, right? I understand what he was trying to say, right? That his love is always increasing, right? But then I reminded him that you can still have a horizontal asymptote. You can still have a limit and always still be increasing, right? You can have a function whose derivative is always positive, and it is going up and up and up. As you move to the right, it does move up very slowly, but it has a limit. It has an upper bound. So I told him that he needs to add some conditions if he really meant it to mean more, like it just keeps going up. It'd have to be unbounded. So we had a little debate about it, because he was like, no, if the derivative is positive all the time, it's got to go up forever. I said, not really. Okay. Anyway, those are the types of conversations that I shouldn't share with people. Yeah. All right, so I don't think it's worth us getting into Chapter 8, Section 2, but it is titled Series. So we are going to begin Series. And I don't want you all to be freaked out about it. All we're going to be doing is taking our sequence, right, which is the list of numbers, and we're just going to say what would happen if you add all the numbers up. Okay, so like you have some sequence, blah, 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 blah. If you take the first number, add it to the second, to the third, forever. So it's almost like we have this big pot, right? And we take the first number out of our list, throw it in there. Next one, throw it in there. We start adding them up. The question is, does that sum overfill the pot or not? Okay, and sometimes it will, sometimes it won't. Yes?
So we're only going to have up to 8 points?
That's what it's looking like.
So then will we do all of up to 8.5 and beyond for the final? Like will we,
That means your final would basically cover Chapter 8.
and 9?
9, that is if we get to it. Yeah. If we get to that, we will try. We're already behind. We're already behind a little bit, but why don't we do this when we meet again on Tuesday, right? Thursday, sorry. Today is Tuesday. When we meet on Thursday, why don't we get through the first part of this 8.2. I'll take a poll, and we'll see if that's sort of stuff you want to see on your test. All right? But if it's not there, it's going to... The thing is, this is a really good place to split it, because from here on out, it's series. So we're talking about series all the way through the end of Chapter 8 now. Okay, please bring next time to class on your formula sheets on the web. There was a thing called series conversion tests that you could print out and bring to your exams. Please bring that to class, because I don't want to have to print out a whole copy. If the derivative of your love function is 0,